A 40 kilogram crate is at rest on level ground. For part A, on the dot, draw and label the forces exerted on the crate while it's at rest. So in other words, a free body diagram. So as with everything on the Earth's surface, we're going to draw the gravitational force, which is F sub g, and the normal force, F sub n, and those are the only two forces acting on it, and we can say that those two forces are equal by putting the little tick marks on them. In part B, are the forces on the crate balanced or unbalanced? Well, since the crate, you were told, is at rest, it's not moving, the forces have to be balanced, which means the upward forces equal the downward forces. Now our worker is going to begin pushing horizontally on the crate with a force of 200 newtons, but friction will prevent it from moving. So draw a new free body diagram for the crate. We're going to start off the same way as before with the gravitational force, Fg, and the normal force, Fn. Those two forces will be equal. Now we also have an applied force, which is horizontal, from the worker pushing it horizontally. That's Fa, and a frictional force opposing that, which is Ff. And because the crate's not moving, those two forces are also equal to each other. So in part D, are the forces on the crate balanced or unbalanced? Well, we just said the crate is still not moving, which means the forces are still going to be balanced. Part E, is the frictional force on the crate greater than, less than, or equal to 200 newtons? We know the applied force, this one right here, is 200 newtons, and since the frictional force and the applied force are balanced, that means that those two will have to be equal, so the frictional force will be equal to 200 newtons. So you can say that to justify your answer, the forces are balanced, therefore Fa, the applied force, equals Ff, the frictional force. So neither coefficient of static friction nor the coefficient of kinetic friction can be calculated using the information given, but for different reasons. So I want you to explain why each of these coefficients cannot be calculated. So let's start with the easy one first, which is mu k. Mu k, the coefficient of kinetic friction, can only be determined if the crate is moving, since that is when kinetic friction is present. But since the crate is not moving, we're dealing with static friction. So with static friction, one of the equations for static friction that you know is the maximum static friction is equal to mu s times Fn. We know the Fn because that's the same as the gravitational force in this case, since those are balanced. So Fn is equal to Fg, the gravitational force, which was m times g, which is 40 times 10, or 400 newtons. So since we know the normal force, if we wanted to calculate this coefficient of static friction, we would just have to know what this maximum static frictional force is. But the problem is that we don't know that. We only know the static frictional force in this case, which is 200 newtons. We don't know that he could be pushing it at a higher with a higher force, like 250 newtons or 300 newtons, which would result in a different value for the mu s. So the one additional piece of information we would need to know to calculate mu s is what is the maximum possible pushing force that he could push the crate with just before it starts moving. And the additional piece of information that we would have to know to calculate the coefficient of kinetic friction is, if you look at the equation, which was the frictional force is equal to mu k times the normal force. Since we know that normal force, if we wanted to calculate the mu k, we would have to know the kinetic frictional force, or in other words, the force needed to move the crate at a constant speed.